This is my physics 2211 lab 2 report. Introduction. The purpose of this lab is to examine projectile motion with and without drag, acting as an experimental look at the difference in projectile motion when there are forces opposing movement. Our system is our ball and the surroundings are the earth and the air. Projectile motion. So projectile motion is whenever you throw a ball in the air and it sort of develops a parabola-looking thing if you have constant force. If you have non-constant force, it'll look a little lopsided. We'll look into that later. But you always have an initial velocity. The drag force will make this sort of a non-constant force kind of situation if it's projectile motion because the velocity is proportional to the change in velocity is going to the velocity is proportional to the force and the force will change the velocity so it'll be non-constant. We're going to be using the position update and the velocity update formula for this because we can take an initial velocity position values and output final velocity position values. We are assuming we have no drag in one of our computational models and drag in the other. We are assuming this because it allows us to analyze the difference between the force if drag's in the system versus when it's not. We are assuming V final is approximately V average for one of our computational models, the one with drag, because we should have a non-constant force due to the fact our velocity is changing and drag is proportional to velocity. We found that our experimental model with drag traveled a shorter distance than our experimental model with it. We found that our computational model without drag traveled farther than our experimental model code. So these are my initial conditions. The ball's mass is going to be constant through both models. It's literally just the exact same in both models as pages, so I decided to condense it into one slide. These are just the initial tracker values, and then these are our time. This is our time. This is our gravity, and this is our proportionality constant for drag. We have constant force here. I didn't even put this in the for loop because these values won't change. In fact, ball M is outside of the it's outside of the for loop. So yeah, we also don't assume that V final equals V average. We have to use the V average equation here because we have constant force. Um, yeah, that's about it here. Due to the computation model with drag, we can assume that we have that V final equals V because we have a non-constant force here. Um, yeah, that's about it. Experiment. Pretty simple methods. We threw a pure ball in the air. We use a yardstick to calibrate tracker units. And we use point mass analysis to get position data in the X and the Y. This is my picture of my experiment. So yeah, these are my initial conditions that I mentioned earlier. Um, these are my comparative trajectories. My green is going to be, this is my computation model with no drag. This is my experimental, the blue, and the orange is my computation model with drag. So you can see the computation model with drag falls short of the computational model with no drag. And then it's a little hard to see, but I do believe that the blue is short of the green. Discussion. So, similarities and differences in our computational experimental models. The computational model and the experimental model show similar behavior. I mean, they're generally parabolic projectile motion. I mean, if you look at this, I mean, it's a little lopsided because non-constant force, like, it won't produce a parabola. But I mean, you can kind of see how it's like generally the same shape. I'm more just talking about this maximum here. I mean, we have like a maximum value where the force changes from positive to negative. Um, Differences values jumped around more in the experimental model, probably because of my poor tracker skills. Terminal velocity. My model did predict a terminal velocity. It was around like negative 1.82, because this will be the point where the velocity levels off. Because if there's no force, um, if the net force is zero, then we're gonna have no change in velocity. And that's what the terminal velocity is defined as. It's the point where the force of drag is equal to the force of gravity. What will happen if we throw the ball straight up? The ball would take a longer amount of time to reach the ground because we would have a greater velocity in the y direction. This will occur because trigonometrically the y component will be sine of 90 times the magnitude of velocity, as opposed to sine theta less than 90. And since sine theta is 1 and sine theta -1 is less than 1, the y component of velocity will be greater if the ball is just thrown straight up. This makes sense physically. I mean, if you just have a y direction, then you're gonna have more force in that direction, or I mean, you're gonna have greater velocity in the direction of greater force. Possible error, poor tracker point mass again, like I mentioned earlier, and a poor choice of value for the proportionality constant of drag. Thank you.